All right. Okay, so now we learned quite a bit about how to identify a Markov chain, but you may also wonder in what type of applications such things can arise. Let me just, to give an idea, let me give an example from queuing theory. So this is a discrete queuing Markov chain. So a Markov chain constructed to describe a queuing system. So the system is described like this one. So we have customers, right? The customers arrive for service and take their place in a waiting line, right? This could be like actually people who want to take a taxi from a taxi stand to go from one place to another. And for example, in let me give the example in a moment. I guess I can give more details, right? During each period of time, a single customer is served, right? And of course, if there is at least one customer present in the queue, if there are no customers waiting in the line, then during that period, there will be no service provided, right? And as I said, this can be just like taxis arriving at taxi stand in an airport, right? People just come out of airplanes, and they just stand in the taxi stand to pick up a taxi to go to downtown. And in busy airports, usually taxis are not allowed to stay there. So what they should do, actually, they circle around, right? Otherwise, it's a big mess. Even in Istanbul, you cannot really move around, right? So customers arrive for services. They join the line, right? And in each time period, a taxi comes, and if there is somebody waiting in the line, just taxi picks him or her, right, and departs. And when the taxi arrives to the taxi stand, if there are nobody waiting over there, just it leaves without anybody, right? So no service is being provided at that time, right? So they don't wait there for somebody to come. They just have to depart, right? And all right, and during a service period, namely when a taxi after a taxi just picks up a person, for example, right? There may still be customers coming and joining the queue as well, right? And we will denote, we will suppose that the actual number of customers that arrive during the nth period is a random variable which we will denote by yn, right? So you will, of course, not know for sure exactly how many customers will join the queue, how many customers will come out of the terminals, right, to pick up a taxi. So that's a random variable for us. And it's an important random variable. If you don't have a good taxi service, right, there will be more customers coming and joining the queues than the ones they really depart from the airports, and there will be huge queues, waiting queues. Everybody will get mad and will shout around, "Where are the taxis? I cannot go home," right? And after that's not a good thing, right? So whoever is taking care of the design of, for example, how often a taxi should come, right, circle around, should take into account actually how many customers can come in queue, join the queue, right, in the same period, during a service period, let's say, right? So these are the important quantities that we should be able to quantify, right? But the problem is difficult because, as we said, a priori, before the actual customers show up, we will never know for certain how many customers will come. So we have to make decisions, policy decisions, before actually customers come and join the queues, right? That's the difficult part. So we are not going to discuss much about how to optimize such systems in terms of, let's say, how to minimize the expected waiting time for a customer, the expected length of a waiting line, right, in such a place. So you can actually tune some parameters. As I said, for example, how often a taxi should come to taxi stand in order to reduce these quantities, right? But you may just ask, is this really an optimization problem? You can send actually one taxi every minute, right? Well, then perhaps many of those taxis will just go without any customers. And they are not going to make any money. And in the meantime, they will run lots of fuel. So the cost of maintaining or running such a system is going to be then expensive. So what you are really looking is actually to reduce the total cost, right? While you are also keeping, let's say, the customer satisfaction at a satisfactory level, right? So the industrial engineer says that the serviceability should be higher than 0.6. It's like the 60% of the time people will be able to depart, right? Within a given window of time, right? Within 10 minutes, they should be able to find a taxi. 60% of the time, for example, that's a serviceability requirement. 60 is low. Maybe you would say that 80, 85, 90. I don't know. If you divide it to 1, of course, then you will have to run all these taxis, and the cost is going to just go up, right? Maybe it is going to be unaffordable. So you try to just balance all these the trade-offs between keeping the serviceability high as well as keeping the costs low, right? But here I'll just describe just a model of how the customers join to the queue, and we will find out that actually this is kind of a Markov chain, and controlling a Markov chain is another subject that we will discuss in another course, right, in the future. Okay, so here then we can say what? So the important uncertain quantities that we should be keeping track is the number of customers who join, right, to the queue or to the waiting line during a given typical service period, right? So we said we will denote it by a random variable yn, right? So yn is going to be, okay, let me see. It's the number of customers, right, who join the waiting line during the nth service period, during which one taxi comes and goes, right? Okay. We'll assume, right? Well, it's a random variable, okay? We'll assume that the random variable yn has a distribution, or, well, okay, probability distribution independent of time n, okay? Service time or service period n, right? Right? Which is given by a known probability mass function, right? Namely, the probability that yn, right, equals k, which is the same thing as saying that this is the probability that exactly k customers, right, join the queue, right, during the nth service period, right, equals to some ak, where ak, since it is supposed to be a probability, is between 0 and 1, and when you sum, well, these probabilities make sense only when k take values between 0 and infinity, right? And we want these numbers to add up 1, right? All right. We will also assume that random variables, right? Y1, Y2, what are they? Number of customers, number of passengers joining the line in the first service period, in the second service period, and so on and so forth, are all independent. Okay, right. And then we define the weighting or the queuing model. So this is going to be the number of customers waiting in the line for service. Okay. Number of customers or passengers. Well, I don't know. What did we say? We started with customers, so let's just stick to that. Okay. Number of customers, right? Waiting in the line for service at the beginning, right? At the beginning of the nth service period, right? So this is just before the taxi for the nth service period arrived, right? So soon a taxi will come. If xn is positive, that means there is at least one person waiting in the line. We'll take the first person in the line, and then this is going to drop immediately xn minus 1, right? All the others will have to wait for the next service period, but in the meantime, of course, there will be newcomers. They will join the queue. Queue then will just decrease by 1 and then increase by the start of the next service period, right? We don't know by how many. It is a random variable given by yn, I guess, right? All right. Yeah, then actually I followed the other way around, but how did we define yn number of customers joining the waiting during the nth service period? Yes, it should be yn, right? So we should just write what I just said, right? So at the beginning of n plus first service period, right? This denotes what? The total number of customers waiting in the line, right? So there are two cases. If there were no customers waiting in the line in the beginning of the nth service period, taxi will take nobody. So it cannot, the queue length cannot go to negative, right? In this case, this is the same as the total number of customers joining the queue during the nth service period, right? These are the new ones. These are the customers who have just joined the line after taxi for the nth service period just left, right? Okay, but if xn was positive, so there were people waiting in the line at the very beginning of the nth service period, so one of them will be taken by one of the taxis when the taxi assigned to that service period arrives. But after that, there will be yn more people, right, who have just left the terminal and joined the queue for a taxi, right? So that's the queuing process. That's known as the queuing process, right? So it counts. It just follows that how the number of people waiting in the line fluctuates over time. If these numbers tend to get larger, then we are in trouble, right? We are in trouble because then that means the airport is not really giving a good service. So people will get anxious, impatient, right? That they cannot really depart from airport on time for they don't always go to home. Sometimes they have to just meet a business partner, so they will just want to. Why? Because at the beginning, this was the number of customers waiting for a service at the beginning of end periods, and the server comes. Each time we assume that the server serves actually one person, right? Okay? You can make it more realistic for the taxi case if there are two people, for example, who would like to share a taxi, then you may actually subtract a random quantity. Right? There are various models depending on how you specify the service system goes forward. Right? But then you also add what? The number of customers who just joined the queue. Right? Okay? We have that. So you look at this one, okay, it's a queuing process, it's a stochastic process. What is a stochastic process? It's just, for the discrete time, it is easier to describe, it is a sequence of random variables. I have a sequence of random variables. The question that I would like to ask is this a Markov chain? With state space, you can guess what the state space should be, right? What are the values that these random variables can take? Number of people waiting in the line. It can be as small as 0, not smaller than that, right? 1, 2, and so on. It can be arbitrarily large as well, right? Right? In principle. So this is, of course, a question at the moment, right? Is this a Markov chain? Right? Okay, how do we analyze that? See, you look at the right hand side. It's again a function of state at time n, another random variable yn, right? So I commented before that this type of things are quite common, and in fact, actually, okay, this is like a function of xn and yn, right? And this is the future state of process x at time n plus 1, and this is, you can say, it is present state of process x. And what is this? This is a brand new information that just comes in, right? As you are moving from time n to n plus 1, it reveals only after you observe the state of the process at time n, right? And this just is, in our case, the number of customers who join the queue, right, during the service period. And we know by the description of the question, this is, right, an independent, right, random variable. A random variable independent of the number of customers who joined the queue in the previous periods, right? This is the y1 through yn minus 1. But then you also notice that x1, x2, and xn, right? Each one of them also admits, right, a representation of this kind. And on the right-hand side, they all depend on previous states or previous values of yn. Right? Namely, these are all functions of, in fact, y1 through yn minus 1, I guess. Right? Because you look at this one, xn plus 1 is related to yn. Therefore, right, y1 is related to nothing, I guess y0 if it exists, x2 to y1 and y0 and y1. And all of them are, in fact, functions of y1 through yn minus 1, all of which are independent of yn. Right? So again, you have what? Future depends on the present state plus a new piece of information, a random variable which is independent of the past and present. That was exactly what we also faced actually in the first example. And we can actually use exactly the same steps to show that the conditional probability that in the future the state is going to be, or the chain is going to be in state j, given all the past and present states of the chain, equals the future state of the process equals j, right, given only the present state, whatever it is. So this process, the queuing process xn, is in fact, right, is a Markov chain on the non-negative integers, right? And you will then want to calculate the one-step transition probability matrix, right? One-step transition. Right? Of, let's say, going from state I to J, right? Let's say currently there are I people waiting in the line. You would like to know that the line goes to J in one period, right? So we denote this by Pij, right? Namely, it was the probability of going to state, the length goes to length. Length of this Q becomes J given that it was I, right? Now we know how to express this x1 in terms of y0 and x0, right? It is like but this is like the piecewise representation, but you may have noticed that that can also be written as, let's say, xn minus 1 plus yn. Is this? No. Yn is always there. Only the first part may or may not be positive. Xn minus 1 positive part plus yn. How about that? Does this agree with that? So if xn equals 0, xn minus 1 is minus 1, positive part is 0, 0 plus yn, you get this. If xn is positive, right? Xn is positive, then of course you have the positive part of xn minus 1 is a non-negative, is itself because it's a non-negative number, plus y, right? Then instead of xn, we can just use this representation. It is xn minus 1 positive part plus yn equals j, given that x0 equals 0. Well, n became 1 in this case. Yeah, let me just replace them with whatever it is, right? And no, what did I do? If n plus 1 becomes n, sorry, so this is 0, this is 0. All right. Okay, and then of course we know what x0 is. It is I minus, so it is I, therefore this is I minus 1 positive part plus y0 equals j, given x0 equals I. And at this point we use the independence of random variable y0 and x0, so these are independent. Right? And there is nothing else random left on the left hand side. Right? So this conditional probability is the same as the unconditional probability. At this point we can just forget about this point. And then this is the same as the probability that y0 equals j minus the positive part of I minus 1. Right? That's what we have to calculate. Right? And there are also, we should split this into cases depending on how I and j are related. Right? Well, both I and j have two non-negative integers, right? They all belong to state space E, which is this, right? So maybe I could write like this and save this space for something else, right? If I equals 0, you get something. If I is greater than 0, you get something else. Right? If I equals 0, this disappears. So this is y0 equals j with probability, I guess, a0, right? We said ak whenever you want to calculate the probability that yn equals k, right? And here, if I is positive, then I minus 1 is non-negative, positive part is itself, so you have j minus I minus 1 when I is positive. Right, Hande? Okay. Then therefore this is a sub j minus I plus 1. Right? So we assume, remember, that we know these numbers. So what did we do? We characterize the statistical properties of waiting line by using the probability law of the number of customers joining the line. right? So number of customers joining the line, something that you can actually study closer. You will just hire a couple of IE students for the summer. So we call that a summer internship. You give them big sheets and they count, right? They count at 9 a.m., 10 a.m., 11 a.m. It goes like this. A lot of data. Then you calculate this, what are these frequencies. By using these frequencies, now we have actually a good idea of how the waiting line is going to fluctuate over time, right? It is going to fluctuate according to a Markov chain, whose statistical properties can completely characterize, as we discussed before, right? The finite dimensional distributions can be found if you know one-step transition probabilities, which we know have this particular form. You can look at the one-step transition matrix P, right? Now this is an infinite dimensional matrix because it starts with 0, goes 1, 2, 3, indefinitely long. In principle, of course, if the tail of this distribution is 0, then of course you will cut it out somewhere. 1, 2, and so on and so forth. It goes like this. There's also 3 here, let's say, right? So the first line is like what? It is just this one, right? It is from 0 to 0. What should have happened here? There were nobody in the line, and therefore taxi is left without customers, right? And at the beginning of the next service period, there will be 0 customers, no customers, if nobody joins the queue in the meantime, which happens with probability A0. Right? I could have actually derived from here as well, but it's even more difficult to follow this. But that's exactly what we did. So this is analytical formula, but we can also just fill in the matrix quickly, like this. Right? Here, there was one customer already waiting in the queue, right, at the beginning of the previous service time. We know that there will be a taxi coming and picking him up. And at the beginning of the next period, there will be 0 customers, no customers, with the probability that there will be no customers joining the queue, right? That's the only way that you will get, you will go from 1 to 0. So this is A0 as well. Then this is A1, A2, A3, right? Now what happens with when you have 2 customers to start with? 2 customers waiting impatiently, a taxi comes, one of them just goes, and the other is still waiting. He has to wait for the next period, right? Right? Can there be 0 customers waiting over there? Let's think. 2, 1. Of course not, because I already said that there is 1, right? So there will be exactly 1 if no customer join in the meantime. If no customers join to the queue in the meantime. Right? From 2, it went to 1. Just before the next taxi arrives, there will be exactly 1 customer if nobody else joined the queue. Which happens with probability A0. Then you can actually argue that then it should go A0, A1, A2. With 3, the second, from 3 you can go to the list, and actually this row just shifts. So all these part equals 0, and you have A0s like this, A1s like this, A2s like this, 3s. I shouldn't do that. Should I? Yes. Except this row. Right? That stays there. So you have A0s, and starting from here, A1s, A2s, and A3s. Okay? Such type of matrix, what you are actually dealing in this particular case. Right. So, as I said, all these things actually will depend on what? Let's say F, the frequency at which the taxis are coming, actually. We just suppress them. When you play, these probabilities will change with F, and then this probability matrix will change with F. And depending on this, then you can, we will show actually, we will learn how to calculate, for example, mean length or long run average, that's the right word, average length of waiting line, right? There is a way to, we will see it under certain when certain conditions are met, the system is stabilized, namely the Q doesn't grow infinitely long. It fluctuates, but it remains somewhere. That's a stable system that in the first place you will want to have. But even if it is stable, this long-run average length may be too large, more than just what is acceptable. Then you use this F to take it to low values. All right? Okay. That's the ultimate goal of teaching such a course. Basically teaching, you have to first understand and formulate the uncertainty and to control it. Control the uncertainty. All right. But let's just stop here. Okay. And look at something else. Unless you have questions. Do you have questions? When is this course going to end? When are we going to stop lecturing? 15 minutes later. But before that, let us look at something else. This is the another topic, first step analysis. I guess this is fun. This part is especially fun, right? I am not gonna give you lots of formulas, but we'll right away start with examples. I guess it's a lot easier to explain these concepts while we are thinking on certain problems. So this is an exercise from your textbook, and it is coming from page 128. Okay? Okay, I'm going to read it for you. So, a coin is tossed repeatedly until either two successive heads appear or two successive tails appear. Right? You flip the coin, two heads or two tails. If it is head, tail, or tail, head, tail, no, you continue. There's no way to give up. Suppose that the first coin toss results in a head. Right? The first one is head. That's what you know. And they want us to calculate the probability that the game ends with two successive heads rather than two successive tails rather than two successive heads. Right? And we also would like to know, on average, how many times we have to play this game until it ends. Right? So it's an open-ended game, of course. You don't know when it is going to end, right? Because you may be out of luck. It may just take 10,000 plays before it ends, right? Although with a very small probability, or it can end actually after the second one, for example, right? On the third one, in this case, right? So let's just take short notes, right? We toss a coin, right? Coin is being tossed indefinitely many times. Until either two successive heads or two successive tails come. Okay? And we know, right, that the first toss resulted in a head. Okay? And want to know, right, two things. Okay, A and B. In part A, the probability that the game ends with two successive heads, two successive tails. And independently, in part B, independently of how the game ends, we would like to know the average number of tosses, right? Until the end of the game. Okay, right? That's the question. All right. there is no sign of a Markov chain around, right? It's just a question that is being set, so, but it is related with Markov chains. So what is the least amount of information you have to keep track around in order to answer the question, right? Now you may think that it's a real game, and you may have actually a bet on that the game is going to end with 2 successive tails. Namely, you may actually offer 1,000 liras, for example, right? Right? And they say that, okay, I bet that it is going to, when the game ends, it is going to end actually with 2 successive tails, and you will get paid 1,000 if that happens. Otherwise, you will lose that 1,000 liras, right? This might not be very interesting, but actually what you are doing with your, you are too young to worry about retirement funds. But when you have some money to save for the future, you put, for example, on what? The B-type funds, right? Type B, type A funds, and so on. So they are kind of bets because you don't know what the outcome is going to be. When you arrive to your 50 years old, you will want to take the money back from those funds. You are betting like, okay, fund B must actually earn faster than anything else. That's exactly this kind of a game. It's a lot more difficult than this one, right? But in order to, principles are the same. If you want to answer questions like, so what is going to be the likelihood that I am going to be rich if I put my money on type B funds? It is like actually, you will just use the similar principles in solving this problem. Okay? Okay, how do I solve this problem? The first question is, well, what is the least amount of information you have to keep track in order to even understand what is going on? Whether the game has ended or not. Right? What is it? So you have to look at the last 2 games. Right? This is the first one. Right? You already know that at the beginning it is a head, right? So the game is going to end, for example, if you observe a head, but you are going to lose because it will have ended with 2 heads rather than tails, right? And if the next toss is a tail, then the game will resume, and the earliest time you may actually win, and the game ends, is the third one, if a tail comes. If it comes head, right, then it is not going to end, it goes like this, right? But while you are thinking like this, you realize that actually you only need to know, not even 2 actually, you only need to know what the result right now, it is tosses, right? So you will just take that and compare it with the next to see what happened, right? So why don't I'm just thinking a lot, why don't I introduce a Markov chain X with the following state transition graph. What was it? I didn't say graph, but anyway. Okay. And so at any time, right, if the chain is in state H, standing for head, right, then we will toss one more time. Either the next toss is going to be head, then I know that the game is going to end because I got 2 heads, right? Or I may get a tail, right? Well, actually, I will have a head and tail, but I know that the game is continuing at the knowing or keeping in my memory that there was a head before the tail. I don't really need that, right? Because all I know that a tail has just come and the game has not ended yet. So that is actually more than what I really need. So I introduce a state that says it is. I just observed the tail and the game has not ended yet, right? And after I get a tail, right? And if I just toss this coin one more time, there are 2 possibilities, right? either I will get a head after tail, but it is the same thing as before. I know that the game has to continue, and knowing that there was a tail before, head doesn't really provide any further information as of regarding whether the game has ended or if it ends in what state, right? Head and the next actually result of the next experiment is more important, so we choose to keep only head and connect it like this, right? From after you observe a tail, if the game is still going on, right? If you observe also a head, you actually continue the game with a head, and then you are now looking for the result of the next game, right? But the other possibility is after a tail, you can get a tail, right? That indicates the end of the game, right? And actually, that's also the desired result. You would like the game to end if you really bet on this particular outcome, right? So now, what I did is just introduce actually a convenient, right? This is not the only Markov chain related with this game, but it's one of the chains with the least number of states in it, right? It's a convenient Markov chain that basically captures the dynamics of the game, right? And the states that are interesting for me, right? Okay. And what are the transition probabilities? So these things show the transitions which have with positive probabilities. And I will also add these things in the meantime. So if you are in HH or TT, you stack those states, meaning that the game has already ended. So you are going nowhere, right? And the probabilities, these are obviously one. And the next result, right, head or tail will always come with 1/2 probability. Did we say that the coin, maybe we should say a fair coin was tossed, right? And I have these things, 1/2 and 1/2 from here, right? Okay. And okay, I now got myself a Markov chain. How can I use this to answer the question? So you define a random variable as, okay, it's a stopping time. This is when the game is going to stop. When does the game stop? The game stops the first time, right, with the first n, at which the state of this chain equals HH or TT, right? That's how the problem was, or the game was described, right? I have that. And by using this random variable S, how can I formulate part A? That's actually the probability, right? It's the probability that the game ends with this outcome. But that's the same as saying that at the time when the game ends, the state of the process is what? At time S, the process is either here or there, right? But this thing will happen only if x at random time S equals TT. Starting where? At time 0, I was in this state, right? This. Okay? That's what I want to calculate. Did we get it? Is this clear how we formulate it, right? Okay. Of course, now I will, to calculate this thing, we need to calculate some other things as well. And working with these letters is inconvenient. Therefore, I am going to give names, or I will assign numbers. I will say that this is my state 0, this is 1, this is 2. I just assign these integers arbitrarily, okay? And then this is going to be like TT was now 2, and the initial state is 0, okay? And I will denote this by u sub 0. I am now defining a function. In fact, for each initial state I will do the same and define u sub I as the probability that if the game ever starts in state I, what is the probability that the game will end in state 2? All right? Okay. The reason why I do that I can actually relate this function, this value to this one, by doing so-called first step analysis. What is the first step? As the name suggests, when you start in state 0, right? You know that the game has not stopped yet. That means you will actually flip the coin at least once. And the way the future results will then depend on the result of the very next toss, right? So you will get either head or tail, right? So we will condition on that. That gives you, that just leads to what is called as the one-step analysis, or the first-step analysis, right? So in general, if you are in state, okay, UI is too general, we can just write actually everything starting with U0. U0, right? So I am looking at this one. So starting in state 0, I know that I have to just toss this coin at least once, right? If after I toss the coin, right, with probability 1/2, right, the result is going to be head, right, head, and you will move to this state, right, and starting from that state, you will again ask to yourself that what the probability that the game is going to end with will end in state 2, right? Or with probability 1/2, right? You will observe a tail, right? And you will move to this state, right? Now you know that you are in state 1, right? And then Markov property tells you that now since you know what the most recent state you are in order to make any inferences about the future, anything that you know from the past is irrelevant because your chain has this forgetfulness property, right? You just left state 0, you just entered state 1. Now that you know that you are in state 1, future is independent of the past. So you can safely forget about that you were coming from state 0 and you ask the same question. Okay, I'm in state 1. What is the probability that the game ends in state 2? That's exactly this with I being replaced with state 1. Right? So you multiply U1. So what I just did is a first step analysis. I just conditioned on the outcome of the first step, either it is head or tail. In both cases, since I know in which state I am moving, right? And knowing the state, the most recent state, past is independent of the future, but the future just is the same as before, namely, if the game has ended, whether it ended actually in this favorable state or not. So we can do the same thing for U1. So here, well, there are some obvious values of these functions. Actually, I should have said them first, right? What is U3? Starting initially in state 3, what is the probability that the game ends in state 2? 0. Because game has already ended. There's no way to get out of this anyway, right? It ended first, right? How about U2? Starting initially in state 2, what is the probability that the game ends in state 2? 1, right? Because as soon as you start in state 2, the game ends, and it ends in the desirable state. Here you have the same thing. As soon as you start in state 3, the game ends right away, and it ends in the unfavorable state. So therefore, probability of moving from into the favorable state is automatically 0. When you start in state 0 and 1, you know that the game will not end right away. You have to just toss at least once, and therefore we can actually write this equation for state 0. And for state 1, right? Starting initially in this state, right? You know that the game will not end right away. You have to take at least one more toss. With probability 1/2, you will get a head. Getting a head after tail doesn't stop the game. Game continues now with the most recent toss H. And once you are in state 0, Markov property says, I don't care in what direction or what path you took to come to me, to this state. Now that I know that you are in state 0, the past or the future is independent of the past. And the future, we are interested in the probability that in the future the game ends, and it ends in this state, right? And then the probability that we are trying to calculate becomes now the conditional that starting in state 0. What is the likelihood that the game ends in state 2, which is given by this, right? Game ends in state 2. Now I is being replaced with 0, so it is U0. But this is only 1/2, right? On the one side of the coin, the other side is what if the outcome of the next toss is tail, right? If it is tail, then you move here, but you can actually argue the same way, right? Now that you moved into a state in state 2, that you know that you are in state 2, as you are making any inferences about the future, past really doesn't play any role anymore because of the Markov property. Now, the rest here is starting is the same as the probability that starting initially in state 2, that the game is going to end in state 2. Even though we know the answer, we can safely write as what? You move to state, that's U2. So you have what? You have, in principle, 4 unknowns. You are interested in this, but there are you ended up 4 equations in 4 unknowns, right? You solve these things simultaneously. Now U3 equals 0 means this just goes away. So this is U1 over 2, right? And now you have U1 connected to U0 and U2, and you know that U2 equals 1, so this is 1, right? And then you can plug this right-hand side into this formula, and that gives you what? You multiply with 1 over 2, all these things. You have U0 over 4 plus 1 over 4, right? Now you have an equation in 1 unknown, right? This thing can go to the left. It gives 3/4 times U0 equals 1/4, right? And from this you get U0 equals 1 over 3. Right? Because with 1/3 probability, if you start with here, you will reach it. So it's an unfair game. Because the likelihood that you will make money in this thing is less than 1/2. You better be careful in playing this thing. So we can quickly set up the equations for part B as well. So you actually play the same game. So here you are interested in the average number of tosses until the end of the game. So you count now the number of times you play the game, right? So we can just now define by V0, or denote by V0, the expected total number of games played starting initially in state 0. That's what we want to find. This is what we want in part B, right? So by definition, so S counts the number of steps, right, until the end of the game, and we are interested in average number of tosses until the end of the game. It is exactly this, right? How do you calculate this? Again, we can use first step analysis. Okay, starting in state 0, right? We know that the game has not ended yet, so I have to just take at least one step. I have to toss the coin. Therefore, I know that I will play at least once. I add 1 plus the remaining number of games that I have to play, right? We did not add anything here. That was because we were interested in probabilities. Here we are counting things, right? Since the game, I know that starting in stage 0, the game will not end right away. I have to toss once at least. So 1 plus, this total is going to be 1 plus the remaining number of games that I have to play, right? So what are the remaining number of tosses I will need until the end of the game? Well, with 1/2 probability, right? I will observe a head, right? And therefore I will move to state 1, right? So I have V1, and with 1/2 probability I will move to state, what is that? 2, right? Here V1, V2, it is just, they are just defined in an obvious way. So expected number of, here, from 0, yes, so this should be 3, I guess, right? From 0 to 3 or to 1, I see. Okay? Right? If I define Vi for 0, 1, 2, and 3 like this one, right? I have that. Again, if you define like this, you can figure out right away what V2 and V3 must be. What are they? If you start in state 2, how many more games do you have to play? Yeah, let us count also the number. Yeah, okay, not the remaining but total. These are all ones, right? Because you have to just toss once. If let us agree that we count the very first one as well, right? And we know V2 and V3. We are interested in V0. Okay, we know what V3 on the right hand side is, but we don't know what V1. So we have to write an equation for V1 as well, right? So when you are in state 1, again the game is not going to end right away. You have to play for at least one more time. And with half probability you will go either left or right. And in the meantime you have to count that very first toss. 1 plus, with 1/2 probability you move from 1 to 0. And then V0 will give you the total number of remaining tosses that you need until the end of the game. And with probability 1/2 you will move to the right, and V2 will give you total number of remaining number of plays, right? So we can just again simplify these things, right? Here we said this is 1, right? So 1 plus 1/2, this gives the 3 halves, right? Plus V1 over 2. And here what do I know? V0, well, we don't know yet. V2, we know 1. It's the same, right? The 3 halves plus V0 over 2. So we can just combine these things. We were interested in V0. This is 3 halves plus 1/2 times V1, which is 3 halves plus V0 over 2. And what do I have here? Okay, 3 over 2, right? There are 2 of them. It's multiplied, and you take the square if you wish. Let me just show my work. And the V0 over 4, right? So this is 9 over 4, and you take this 3 over 4 times V0, right? And V0 becomes 1. These cancel, and you have 3. You get this. On average, you need to play 3. On average, you have to toss 3 times before the end of the game. Okay? Does it make sense? Okay. Okay, that's great. So a couple of similar examples, or I shouldn't say similar, different examples, but where we use, again, the first step analysis to solve the problem. So we are going to meet tomorrow, right? Tomorrow at 9:30 here again? Okay, that's great. And I'll see you tomorrow then. Unless you have questions. Do you have questions? Yes. Yeah. Why did, say it again, why did I add?
We said 1 plus.
1 plus. Where, you mean this?
Yes.
This? So you are in state 0, right? Here, right? So you know that you have to play at least once, because the game ends if you start here or there. You have not started in either of those states. Until you reach to one of those states, you have to just toss at least once, right? So I toss once. That's, before I forget, I add that. So V0 is what? The total number of tosses you need until the game ends. It is like what? One toss while I am in state 0. What is this? And then plus the remaining expected number of remaining number of tosses. Right? This is the remaining ones. Okay? Any other questions? That's my phone. Sorry about that. Huh? Is that all? Okay, then I'll see you tomorrow.